Okay, hello everyone. Let's start our meeting today. Who's gonna go first? We have.
I think we from University of Tartu, we kind of promised to do a little presentation of our changes.
Yes.
The OpenPlanner.
Yeah.
So we can start. So the plan from our side was that we kick off with a short video that shows the current functionality that we have and how the car behaves, what it can do and what it can't. And then we will continue with Edgar and Max showing the changes they had to do to make this thing happen. And I hope we can do it in half an hour or so. But as a very first thing, as long as I know, the sharing the videos in those apps doesn't work too well. So I think it works the best if I paste the YouTube URL to the chat to all of you. And I will kindly ask you to watch this video for the next 7 minutes. This is a short introduction of our demo drive in Tartu. And I will start myself too, and then we will continue in 7 minutes after the video ends.
Okay, we will start watching the video now.
Yes.
Are you going to give us a command when we should click play, or?
Sorry?
Are you going to tell us when to click play? So we all are the
yes,
same.
You can click the play right now. I think we don't have to be ideally synced with this. So I hope everyone is finished with the video. Thanks for watching. I hope it was at least a little bit give you a background what we are doing here in our autonomous driving lab in Tartu. Now I would like to give word first to Edgar, and he will talk a bit about different changes that we had to do for the velocity control and trajectory control. And then Max will talk about the changes he needed for the obstacle detection. So yeah, the floor is yours, Edgar.
Hi, so I'll share my. Ah, it says that host disabled participant screen sharing.
1 second.
So can you?
Ah,
Yeah.
Okay, go ahead.
Okay. So can you see the screen? Should be working.
Yes.
Yes.
Okay. So mostly about speed control and trajectory, actually, also as Tambet said. So so this slide kind of represents where we started, or how it's kind of in general level goes on with OpenPlanner. So we have this localization, and as an RV's input, we put the destination point. Then the global planning will happen, and as a result, global path will be kind of produced. And in this step, so this is done only once before we start driving. And what happens here is that the global path on the map will be found. So then the path will be smooth and there is resampling going on. Then the cost is calculated based on the curvature of the trajectory. And then reference velocity from map is taken. And then this cost that is calculated based on curvature is used to adjust this speed. So we will have this speed profile for this global path here. And at the end, there is another smoothing of this speed profile going on. Yeah. Okay. So then when we engage, the driving starts. And this process is now iterative, so it constantly updates. We are extracting this local path there. Also, every iteration step, the behavior state is updated. There is this function get velocity ahead that looks ahead and kind of modifies the speed profile for the global path during the runtime. And there were also PID controllers to update the velocity also in the OpenPlanner. So the first thing we did, we removed the PID controllers from our workflow. And it's not that there is something wrong with them particularly, but it's a kind of combination of many things. But maybe one of the most important reason is actually that since we have our car bought from autonomous stuff, and then when we run OpenPlanner, then there are these twist gates, twist filters, different things in between. And finally, when we reach SSC module, then it also has actually PID controller in it. And currently with not currently, but then when we started running it with two PID controllers simultaneously, we were really in a trouble to kind of getting, as you see these oscillations here. So they started to interplay with each other. And of course, there were some other issues also during that time. But yes, the main thing to look here is this red graph, the final velocity that the car was actually driving. And you can see these oscillations happening here. So we got kind of eliminated PID controller because we already had it. So the next thing is we skipped this cost calculation based on curvature. And that also meant that we didn't use this cost to update the speed profile. So the problems here were that having this cost, it was hard to know. For example, do you see also my mouse on the screen when I move it?
Yes.
Ah, okay, then I don't need to. So, for example, this turn here, let's say we have official speed limit in the city, 40 kilometers, 50 kilometers per hour. That is close to 13 meters per second. So these red numbers show here the speeds in meters per second. But if we put here all the way as the official speed limit is, let's say 13, and we rely on cost, then we see the final outcome only when we run OpenPlanner, whether in simulation or we actually go driving. We don't know beforehand what will be the speed in this turn. So it makes kind of it a bit more complicated. And furthermore,
Hello?
We lost you for a moment, Edgar.
Yeah, can you back 5 seconds?
this curvature is a bit differently, then the speed will
I don't know, Edgar, if you hear us, but we lost you,
actually
and maybe you can go back 10 seconds.
Edgar, there is a problem with the sound, with your sound. Ah, he already disconnected. Ah, he had a.
Hopefully he will be back in a moment.
Okay.
I think he had some internet connectivity issue at home. Yeah, maybe in the meantime, if you have any questions about the video or the setup we have, okay, Edgar is back.
Yeah, I have some questions. Can you hear me properly?
Yes,
Yes.
but Edgar is back. Maybe we let
Okay.
him to finish his thing.
Okay.
So Edgar, are you back? Edgar, all cool? He seems to be frozen.
Okay, until he's active, we can discuss.
Yeah, Matthias, you had some question.
First of all, very, very impressive. Looks really good to see it running in real traffic in a real world. That's very impressive. About the positioning, just a quick question. What positioning system we're using? Is it the Novatel system or?
Novatel.
Okay.
Yes.
So we're
Novatel,
using.
The Novatel, and really crucial for us is the RTK, because in Estonia we have the whole Estonia covered with those RTK stations by the government, and as an academic institution we have free access to them, so we get RTK basically for free, and it has worked really well for us.
Yeah, same in Germany. We're also using RTK with a Novatel system. Edgar, are you back now?
Sorry, Edgar. We, if you are back, then
so
maybe
can
we
you
can
hear
continue.
me?
Yeah.
Yes, we can hear you now.
Yeah, okay. I think my internet is also bad. Yeah, I dropped out. Okay. So, and the third reason we discovered that no, because of
We
these
might not have
different
heard the reason 1 and 2, or at least 2.
okay.
I'm not sure.
So yeah, so the speed, as I said, if we would map all the lanes with maximum speed limit and then rely on the cost, then cost will be calculated and the speed will be adjusted for this curve. So the first thing is we will know it only when we run OpenPlanner and try it out on the simulation. So, but we would like to know it before. It would be much more convenient, so we can compare with our speed when we drive through it. Then this cost calculation is dependent on how the trajectory is actually drawn. So slight differences in digitizing the lane here will affect the cost and it will affect the speed. So if I change it the next time, the speed might be a bit different there. And the third thing is that although, so we had one test area in Tartu, and then we adjusted these parameters, the cost calculation parameters that some of them are hard coded in the code. There were some ratios calculated and some are as a parameters in the launch file. So we adjusted them for Tartu, but the road or demo route in Tallinn, in another city in Estonia, was kind of a bit different. The turns were sharper, and it turned out that this tuning didn't work in Tallinn. So we had to somehow made it more convenient for us. And that's why we dropped this cost calculation and we actually used kind of the speed profile. We put the suitable speed. So here we can see there is 5. So it means that in this turn, we want to be driving 5 or less than 5 meters per second, but preferably with 5 meters per second. And here we can see that from this, starting from this point, we want to be 7 or less, and so on. But we will see a bit further how it kind of, we had to change some other things also in order so it would work for us.
Yeah, actually,
So
to just comment on this point,
yeah,
Elastic, they do the same. Tight corners, different corners give different, because this function is not naturalistic or just a way to solve a problem when the map doesn't have the proper speed information. But if the map, because we had different maps in Japan here, when each segment or each lane, it has a proper speed information. So this was a temporary solution. What you did is the correct thing, is like add the speed in the map and use that directly without using this kind of speed profile on the trajectory itself.
Okay. So how it now works for us, so we can imagine that this red line here on the graph would be using the cost function. So actually we didn't totally throw it away, we made it optional. And there is another kind of side work. One student is actually training a model to from our data set. So what is the curvature and what is the speed should be, and we are actually replacing that function with ours. But yes, let's say this red one here is the speed profile when using the cost calculation. And the blue one is actually all the speeds. So the starting point of this graph is here. So we see that it starts with the 13 and then it drops to 5. So this section here is driven with 5. Then there is 6, there is 7. Then we allow it to speed up, but it don't manage because it needs to slow down for this turn. Here it's 4, but we can see this very corner, like lots of these jumps here in this initial speed profile. But in order for it to work, so the next thing what we did is we modified this function get velocity ahead. So what it originally did currently is it retrieved this minimum velocity within look ahead distance. And yes, look ahead distance, it depended on our speed. So if the speed was smaller, the look ahead distance was smaller, etc. But it also didn't work very, how to say, deterministically. If we, for example, look at this kind of speed profile and the look ahead distance is here, then the minimum is this one, and it will say that, okay, I want to drive with minimum speed starting from here, and it will start to decrease. But what we did is that we kind of made it to look all the speed changes within the look ahead distance and calculate the velocity profile needed to achieve this speed with constant deceleration. So when I put here these lines, we actually see that, okay, there is a speed change, and to drive at this point with this speed, we need to do this kind of deceleration. And for this point, we need to do this kind of deceleration. And now when we drive on, when we reach this point, we will start to follow this line, then we will drive on, and here we will start to follow this line. So, or imagine if we are having, we will be, for example, somewhere here, we would have option to select 3 speeds, this one, and this one, and of course, the minimum speed is selected. So what we are doing now is we are having this look ahead distance, and we calculate this constant deceleration. Using constant deceleration, the speed decrease needed to achieve this speed at this point. And so the speed profile will be modified during the runtime. So if we are coming back to this speed profile here, this blue one, then what actually happens is that so this graph is a bit bad in this sense that it's done using simulation. And in the simulation currently, we don't have any control for speed increase. So the real car would start accelerating slowly with some rate that is predefined. But in the simulation currently, it goes straight away to 13 as the maximum limit. And then we have calculated that we need to be at this point with this speed. So we will start to decrease here. And also here we will decrease for this point and so on. But the real car would drive something like this. So we will start accelerate with a limit of 1 meter squared per second. Then we will follow this. Then we will also slowly accelerate. So this is currently how it works for us at the moment. So we generate this initial speed profile, not taking into account cost at all. So we can map these speeds, and we more like map it like the way that in this turn we want to drive with 4 meters per second. In this 90-degree turn, we want to drive 3 meters per second, and this turn is here. Okay. So what
I
else
wanted to ask about the
we
peaks
did? We also then
on this figure.
yeah.
The peaks on this figure are just
Yes.
plotting artifacts, or
No, it's also the simulation problem currently, because when this speed ends here, then in the first iteration in the simulation, the car just jumps back to the maximum. And then within the next iteration, we have this look ahead, and it calculates that we actually need to be in this level, and then it jumps back here. So this is this simulation problem that won't happen with the real car. because we can't accelerate this fast in the real world. I just didn't have any bags to extract so I'm working at the home office and didn't have any bags to extract yesterday. My internet is not so good. They are quite big. So yeah. So these are artifacts from the simulation. Okay. So we also skipped this at the ending. And for this one, we had problems because it shifted some attributes of the lanes that we had initially mapped. For example, we use lane type as a source for blinkers or indicator lights. So we see here that this red denotes the area where we would use right turn, so right blinker, and the green is the area for left turn, so it's the left blinker. But when we use the smoothing at some point, it shifted these areas, so they didn't remain here, but they were brought backward. So we would start, for example, in this roundabout case, we would start the blinker, for example, maybe here. So quite a bit earlier than we would need or would usually do. So it made some things a bit more, again, undeterministic. So we
Yeah,
moved the
actually,
smoothing.
to comment on this, the smoothing function had this problem.
Yeah.
It's fixed now. It used to like take the first attribute of the first waypoint or like a segment, and then it repeated with the waypoint resolution distance. So now it gets the attribute of the closest waypoint, and then repeat that until the attributes changes. So this was I actually because like I didn't get any problem because I didn't go to this checking the attributes of the waypoints, but someone told me that there is a problem and this is fixed now.
Yeah, actually, I think we communicated about this and you said that there is a problem and it fixed, but we actually implemented it so that we do this during the map drawing. So we are drawing our maps in the QGIS and we implemented some smoothing script there. So we actually, no, the initial lanes from our map are already quite good. So they don't need much smoothing. So we haven't
Yes,
kind
great.
of re-enabled it anymore.
Yeah, again, again, the same problem is that if you have it good in the map, then you don't need to the smoothing options or speed profile options. These were for the badly drawn maps. So yeah, that's the proper solution. And I like the approach, the previous one for the velocity, get velocity ahead. This one, I think if you, we can talk about if you can post a merge request about adding this to OpenPlanner too.
We were actually thinking also, we have been thinking but not implemented to do it also for acceleration, because currently, as you see on this graph, this acceleration happens in simulation like instantly. But to do this on this, but we haven't done it or hasn't been so important at the moment. So the next thing is we also updated how this. So this is a bit of a smaller thing, but we changed the logic a bit here. How we update behavior states. So what we did, we actually moved calculations for different kind of, let's say, scenarios, because they are a bit more generic than states. But we calculate follow speed, stopping speed, and forward speed in calculate important parameters for decision making. So before making a decision which state to choose, we have also calculated these, and we use these to make decisions about how to change the state. But I will explain it more thoroughly a bit later and after this slide. So what else? We added some transition to kind of state machine. So we added the possibility to go from traffic light stop state to follow and stop sign stop to follow. And why we did that is very simple. We had sometimes these kind of problems. But now you can also see that, so we approach the stoplight.
Mm. And it changes before you stop.
Now we have calculated that forward velocity, if there wouldn't be any of this, we would drive 11 meters per second. That is our kind of limit in the city that we use. So if there is a traffic light with red, then we know that the distance to the stoplight is this. We use this constant deceleration model. We calculate the speed profile, and we get that at this point we would need to drive with 9 meters per second. And now we have car already standing here with velocity of 0. So we calculate also taking into account the distance, its speed. We know that to stop behind this car in a safe distance, we need to drive currently 8 meters per second. And now actually in the behavior state machine, yes, we check also other things like what is the traffic light and so on, but it's easy to compare and select the minimum speed of these. So the minimum currently is 8. So we need to go to the follow state. And no, this is actually quite useful in the cases. Let's imagine that our perception is somehow distracted and we don't, there is rainy day or snowy day, totally possible here in Estonia. So our perception fails to identify object clearly, and we identify it only after we have gone to this uh, traffic light stop mode. And out of this mode, it was only possible previously when the traffic light went green, then we will go to forward, and other way out was only if we make a stop. But currently the stop would have been here. So it means that we couldn't go to follow mode, and the stop point was the stop line, and we would stop where this car actually is. It means we would have crashed. So we would add this possibility that we can at any place go to the follow mode also. And yes, so if the perception fails and we have this API-based traffic light access, so for example, we go 50 meters before the traffic light, we go to the stopping mode already because we know it's red, we start, and then in 30 meters when we actually recognize that there is a car, then we have an option to go to the follow mode. And another scenario, for example, if this car actually drives very fast, but it's closer than the stop line, then because its velocity is very big, the follow velocity for us or for ego vehicle will be bigger than the velocity that is needed to stop here for this stop line. Then again, in this behavior state machine, we can easily select this state as a traffic light stop. And very quickly, I put here also how we calculate, for example, this follow velocity. Here we use the distance to object. Then we add this kind of reaction time, or we think of it as a reaction time. We interpret it as a seconds, like let's say 1 second or 1.2 seconds. We multiply object velocity with it, and then we subtract additional braking distance. So when the car is moving faster, this kind of normal distance that is named here. Normal distance we want to keep with another car. So when the car is faster, it will be bigger. When it's slower, then it will be smaller. And based on this normal distance, we input it into this equation, and we calculate kind of our speed needed for follow mode. And the last slide here is there are some other smaller changes, but one example also here with this situation again, there is a traffic light, and sometimes it happened, for example, there is a bus in this adjacent lane, and since there is one lane here, it's branching here, and if the bus stops here and we can't get past, but we are using, for example, this radar-based object detection. So radar-based is not so good laterally. So it would say that object is there, but it means that we can go past it, but we actually can't because the bus corner is really close to us. So we will brake and stop. And previously there was this logic when we do this stop, it means the same thing, that there is a traffic light and we go to this traffic light waiting state, and then it was assigned as a previous traffic light ID, which meant when we start driving again, this traffic light was already as previous traffic light. And although it was red, we didn't stop here anymore. So we removed this logic also from there. And other scenarios, it might happen with misclassification by camera, or maybe if there is this short cycle of green, but there are many cars and we won't get past through this traffic light within one cycle. So we do some stopping there, but yeah. So thank you. This was my kind of some insights what we have done.
Thank you very much. That's really like detailed and I think really good ideas or changes to OpenPlanner to the better. I like the speed profiling changes. It's a very important and very good. And also the final previous traffic light stop and go and stop. I agree with you. This one has an issue, and I didn't actually try to solve this. So yeah, this is needed to be solved. That's a good solution. One comment about the changes in the behavior, adding the velocity, the deterministic velocity, that increase the complexity of the behavior selection a lot. And I try to minimize this complexity and make the transition as simple as possible. Minimize the branching between the states. One reason is to add a new state. It will be a nightmare to handle all these parameters, and so to be able to test the new state. That's why some of the behaviors I just take it outside the state, and you rely on the velocity. The calculated velocity is still reliable. So calculating like discrete velocity for each state, I think it will. I maybe in your case it didn't, but when we change like target velocity or change the car or the sensor, the controller itself on the car, this assigning, you will need to change all these kind of assign constant velocity and add a lot of parameters. So to tune that, you will need to understand a lot of the details in the behavior change strategy first, and then to be able to understand the each velocity, what's the target, and in which case you want to increase or decrease. So although it's working for you and it's a practical solution, but from my opinion, we can find another generic solution, which we don't have to handle the velocity inside the behavior state selection.
It's so and so, because previously what was done, no, the same case with the stop line and car also stopping for the same stop line, so it's in front of us. So previously it was you have to check it somehow, and then you will check it based on distances. So the distance of the stop line is 10 meters, distance to object is 9 meters. But now you don't know if the car is, you have to know also if the car that is closer to a stop line to you than a stop line to you, then is the car driving or is it not? So actually the speed calculations include all these distances. Because
yeah, I understand that.
Yeah.
Distance was more why I choose distance, because you can convert distance to velocity, and it's more reliable because you don't have radar all the time. If you have radar, velocity, yes, I agree, it will be the best way to go with this solution. But most of the cars we have or the experiments we did, we had only LiDAR. And LiDAR or camera, it can calculate better the distance more accurately than the velocity. This is the main reason why distance is essentially the base. And then you can, if you have reliable velocity, you can maybe you can calculate the velocity and compare it to your calculated velocity from the radar. One thing I actually let me just the main problem was in the stop the switch between the stop state and the follow state, right? And the traffic light stop state and the follow state.
Yes.
Yes, this is so as I said, you can maybe you can think about it. You can just make it to be able to switch and switch back, to switch to follow and switch back and go from follow to wait or stop. So this will be the case. I think what you did is exactly that, but with adding the velocity as an additional complexity selection criteria.
Yeah, maybe short comment. I agree with you also, and we haven't thrown out all the distances from the comparisons. As a safety measures, we definitely have also that if the car is closer than this, then don't use only the speed and so on and so on. So yeah, these are also there as a safety measures. Yeah, it's not only the speed we are comparing.
Yeah, that's yes.
I just wanted to say that I greatly underestimated the length of those presentations and discussions. So unfortunately, I have to leave. I have another meeting coming on, but I think Max from our side also has a presentation lined up. So
okay.
I hope you will have a good discussion and
thank you. We'll share the video with you. You can actually maybe you can if you have comments, to be happy to get your comments back later. Okay, thank you.
I can stay for 5 more minutes.
Okay, so to wrap up the discussion about this, I will check again let's next time I will give you like my counter design of solving the main issue without adding the complexity I said it will add. Because actually the main one objective Matthias will talk about now is to be able to add additional behavior states easily and be able to select from a configuration file between those behavior that you want this behavior in this demo now, and you want to take out this behaviors from the demo. So these are like to be able to pick up behavior dynamically. We need to make it as generic as possible. So maybe we'll have next meeting additional with also the Matthias will what he will introduce today about adding new behavior.
About the behavior state. So Edgar, thanks for your thoughts about it. We've experienced exactly the same, like we can't handle stoplights if there's someone in front of us, so that wasn't working before. And therefore we were just using the distances like Hartem supposed, because it will be more easy in a way. And maybe we should have a separate discussion on how we want to handle the stoplight. So basically what we did, we put in the follow mode, basically adding the follow mode to the stop line mode. So we detect the vehicle. If we go towards the stop line, if we detect the vehicle in front of us, which is a lower follow distance, then we go basically to follow mode inside the stop line mode. And the yielding thing is something else.
Okay, yeah, we can discuss this. I think Edgar will have a lot of comments when you introduce your the new yielding behavior.
And the yielding is not done yet. I think we still have to wait a little bit more until it's finished and I can present it.
Yeah, just we talk about like we can just talk what we want to do. We want to introduce like when you're merging or when you are stopping in a traffic light, like and you already have the way the proper the right way to go, but there is a pedestrian or another vehicle or a bicycle or a car coming from the other side, so you want to yield for that before it crosses. So this behavior now it's not in the OpenPlanner. It just detects that it's dangerous and wait for that. So we want to add meaningful state called yielding for these kind of situation and mark in the map. As you showed in your video, you can't go left from the stand stop when there is cars coming. When we have yielding behavior, I think merging will be natural, or the car will wait until it finds the proper distance or the empty distance chance to be able to go to the target lane.
Yeah, I can share the screen and show a video of the current state we have.
Okay, sorry, Matthias, can we go after Max?
Yeah, sorry. Yeah.
So that's it.
Thanks.
Edgar,
can you hear
do you
me?
have anything else?
Yeah, Max, go ahead. We hear you.
Okay. Okay. Very good. Thank you. So I will share my screen. Can you see the screen?
Yeah.
Okay. So thanks everyone for being here. So I'm Max, and I will talk about the small OpenPlanner edits I made. So two main things in the obstacle detection and the swerving. So I will go into detail into each of them. So what I did, it was even still in the time of the first OpenPlanner before the update to OP2. I totally rewrote the calculate distance cost function. It's the function that takes the obstacle points and we'll then assign them on lanes and output lane blocked or not, and with the cost. So mostly I did it to optimize it, because it's a function that like it will loop a lot. And I removed all variable declarations like outside the loops, and I got like a better performance, and also added the tracking on the center rollout, like the global path, and also on each other rollout. So we will get like the distance of an obstacle on a distance from our car to the obstacle on each rollout. And then we have, I also took the filtering you did already. And for example, like an obstacle that is behind the car that before a certain distance will be ignored. Also, if it's after the goal and slightly even a bit after even the goal, because the problem we have at the moment is that the distance to obstacle on the lane is quite accurate, but for a reason that we don't understand really yet, the distance to goal is not really accurate. When we are far away from the goal, the distance is overestimated, and when we get closer, it's underestimated. But the distance to the goal, the distance to the obstacle is correct. So that's one problem we have, and one problem why I couldn't so why I have to add a relatively big distance between the for an obstacle point to be ignored after the goal. Also, if the obstacle is too far laterally, and so right now, and I think it's still the same in OP2, an obstacle will be taken into account if the obstacle point perpendicular distance relative to the rollout is smaller than the safety box width, half the safety box width. And in OP1, when I did it, it was not taken into account on the rollout, meaning that if we went out of the way, if we went out of the lane, and then we went back, like we followed the roll-in into the road, we could hit an obstacle. So now, because we track on each roll-in and the way back to the road, we can detect obstacles. So maybe it has been updated in OP2, because I just like merged this function I wrote in OP1 into OP2 when we updated. So the obstacle detection at the moment works like that. So we have our safety box in green here. We have the lane, our path in blue. And if an obstacle is present in this area that is like light red, we will stop. And it works quite okay if we are straight, but the further the curvature of the road, the more problems we will have, because then the space our safety box will occupy will go beyond those limits. So for example, if we just try to take a sharp turn, and we have had a sharp turn like in Tallinn, like in city center, we are in a place where the obstacle points will not be taken into account before they enter the safety box and we emergency brake. So this got dangerous in curves. And for example, when we would start to turn right and the car is stopped in this area, then we would go very close and stop when the car is in the safety box. And then our operator would need to take over. So one solution that I try to implement is to roll the runout, the safety box on the path on each waypoint. So you get here that it will increase this area of we need to take into account for the obstacle point. So I did this, and I used the point in polygon algorithm that was already present in OpenPlanner to check for an obstacle point. So here it increases the area where we will consider obstacles. And so this has several problems actually. It's closer to the actual area that the car will take when driving, but it's not exactly correct because it still considers that the car will be exactly on the path. And if we use, like even with MPC that we use right now, we still cut the corners a bit. So the area on the outer curve is overestimated and the inner curve area is underestimated. And the processing power to do that was a problem. Like it introduced too much delay because we had to, for each rollout and each obstacle, we have to loop for each rollout, each obstacle point, and each waypoint. So we couldn't use it. It worked in principle, but we couldn't use it. It was taking too much processing power. And if an obstacle was between two safety boxes, then it wouldn't consider the obstacle. So it's not an ideal solution at all. One other solution would be to simulate the car on the path. So you can see here that I run the simulation and I outlined the area that the car takes. And you can see here that in the curve, something very interesting happens is that even though it will cut the corner a bit, we see that the area on the outer curve gets bigger. It gets bigger, but the area on the inner curve, it gets smaller. So here we are even a bit closer to the real path of the car. But this also has some problems that I think can be relatively hard to solve. We will still have a hard time to guarantee the same behavior as car. We will have to modelize the car a bit more accurately than the OP-Planner simulation. For example, take into account acceleration limits and this kind of stuff that is not present yet. We might need even more processing power, add more complexity because the simulation will mostly have to run in a separate thread or separate node. So introducing again more latency. And also this will be hard to guarantee stability. So we would also need a fallback, increasing complexity even further. So yeah, this is one of our problem, and this is one thing that is problematic for us, especially in city driving. And so yeah, we encountered this problem. So we have to take over sometimes because of it. So then about swerving. So I played with swerving for a lot, and we got it working in principle, meaning that you can see on this picture that there is a car that is parked on the side of the road, and so the swerving sees it and will swerve left. And so this will work. The car will swerve left. It will go on the left rollout, and it will continue on this rollout. And the problem it created for us is that when we went back into the center rollout, there is technically enough space for a safety box, but as you can see here, it leads us in an uncomfortable situation where the safety box gets too close from the obstacle. It can be for several reasons. First of all, only because a human would just take a bit more space. And also because when we get very close from the obstacle, the LiDAR that is on top will have a hard time, for example, to see the bumper that is close to the ground or etc. So this is one of our problem, and that we have a few solutions to solve it. For example, introducing a delay before going back into the center lane, or also one idea is wait for each lane to be before switching to a rollout, wait for the lane to be free for a certain amount of time, or when we are taking a rollout, when we are in a rollout, increasing the safety box, meaning that the further you are away from the center rollout, you will have a bigger safety box. Or the cost function could take into account the previous obstacles and the previous cost of the lane to make it decrease with time. So those are solutions that we haven't implemented because it went a bit out of the priority at the moment. So also, so this was about going back into the center lane. But now let's talk about going out from the center lane to outer lanes. So can you see the video correctly?
Yeah.
Okay, so we are using LiDAR, and LiDAR is okay, but sometimes it has a bit of noise. Sometimes it will detect curb. Sometimes it will have the ground removal might not be accurate. And the problem we had is that you can see that very briefly, the selected lane gets purple, and it will try to switch like very quick to, and the big problem was unpredictably to other rollouts. And the problem it introduced is that as we don't have prediction, it was not acceptable to have the car sometimes unpredictably switch rollouts and go out of its lane, while a car might be taking over, while another car behind us might be taking over. And this led to dangerous situations. So here is an example where our driver took over, where the car started to go out of its lane because of noise. And it seemed like very hard to eliminate all the noise, even with radar. It would require a lot of pre-processing that we don't have that accurate yet. So the problem is that it jumps from rollout to rollout too fast. And how can we select like a truly safe rollout? So I thought about a few solutions that I'm thinking about implementing as soon as this gets higher priority. Is that first of all, we could try to avoid standing obstacles only. For example, if a car is driving slow, we will just follow it. Or if we have a car that is parked a bit bad and is a bit on our way, we will stop, wait for a time, and then take over. It would leave some time for the safety driver or the human on board to check the situation, like it would do maybe in real life. Also, one problem is that swerving is not safe in all areas. For example, swerving in curves might not be the best thing. And also enable it only when prediction is enabled. Another thing would be to add some delay to rollout selection. That the rollout has to be clear for some time, and that's same as the function that takes into account the previous costs, that the cost will decrease with time without, if there is no obstacle detected on a lane, then the cost will decrease with time and not quickly. And that's all for me. I gave a lot of problem and very few solutions, but still, thanks for your attention.
Actually, thank you. I have solutions for you. If you check the last week's presentation, if you enable the prediction and you can detect the cars on the left and right lanes, you will not do the switch, because the obstacle detection is not what you use until now. I think the old one, OpenPlanner 1.5 is static obstacle detection. But if you enable prediction, you will have the extracted trajectories from the map. So if the car driving on the left or right, then they will have a long trajectory depending on their velocity, and you will not be able to go left this kind of change, the swerve, this will be this hard swerve, because it will detect the one on the left. So trying with enable prediction, this can give you a better result. Also, I don't know if you checked the new trajectory evaluation. There is a better function called get relative info limited, which actually calculate better according to the direction. One problem actually we still have, because the perception doesn't give a proper obstacle direction heading. This is difficult. So direction of the obstacle, if we have it correctly, everything, and have good tracking, then all the solutions which have been tested on the simulation will work as expected. The main problem is the perception. We don't have reliable heading, and the tracking, we don't have reliable tracking to get the proper velocity of the obstacle. But I encourage you to try the OpenPlanner like 2 feature on the same map you showed me, on the same data. So you can extract the trajectories for other vehicles, and this will be used in detection, in the evaluation of the trajectories. This is one solution. Second, if you check the simulation, forward simulation and backward simulation, this can help you with your simulation solution actually, because I did, there is like a small function, 3 lines of code, which give you output, simulation output using OpenPlanner, driving on the trajectory, especially in the turns, which actually still doing swerving and updating the current selected lane on the tight curve is still a problem. So the one solution is, I suggested for ADAS Tech, is to disable the swerving on the curves. So how we can do that? There is, you can add a flag in the map, and then you check it. Like currently it's not implemented, but this is the proposed solution, is to use the map to add a flag, and then in the curve doesn't use it. Again, automatic one, I think it will produce the same problem as Edgar explained. We can check the curvature of the automatically. If the curvature above certain limit, then we can disable the swerving. Those are 2 solutions. Actually, the one automatically disable the swerving is currently in OpenPlanner 2. So you can check that too.
Okay. I think we need to even update again our OpenPlanner 2, because it's like several months old already.
Yeah, those solutions may be recent. So
yeah. And
try the one on the OpenPlanner 0.1.13, the latest, on my GitHub repository. Try it on the simulator, and maybe you can send me a video and tell me your comments. We can discuss that.
Okay, it would be very nice. And I will comment your idea of marking areas on the map for disabling swerving. I think at the moment, because we rely mostly on maps, I think this would be a good enough solution for us, especially because we already have pedestrian crossings marked in there, and that we also plan to disable the swerving in near pedestrian crossings.
Yeah.
So having like unsafe swerving zones seems to be, at least for our use case, something.
If you define the area as intersection or crossing, this is what Matthias will
I
talk
think
about.
that's the best point right now for me to give you a quick
Okay.
overview.
I prepared the
Any
transition.
comment from you, Max? Before we switch?
Not at the moment. Thank you for attention.
I have just one very quick question. Is there a dedicated tag you suggest or to disable swerving on the map?
If you're using vector map or linear 2, then we will try to use the existing one. We don't have option. But actually, it's a better way to use the areas as not the maps. We use the area type, the crossing or intersection or customized area. In vector map and linear 2, there is a customized type for the area that we can play with.
Okay.
Okay.
Okay, so
Matt?
about the areas, I'm not done with this yet. It's just a work in progress, but I think with this video I can just show a little bit what's going on right now. So this is our eco vehicle here. We're starting in the forward state. I just go down a bit. And we're going
if you
for the
see
traffic.
that these yellow dots, yellow circles, these are the predicted trajectories for the vehicles. So.
And yeah, then we are waiting there until the traffic light switches to green. And as soon as we enter this intersection here, you can see the intersection zone with these light blue lines. We will transition to a yielding state, which you will be able to see now. Now we say yielding here, because now yielding is basically just based on the information if our trajectory is blocked and if we are inside an intersection zone, then we switch to yielding. This is just a very, very basic and quick implementation we did to enable yielding, because we had cyclists coming from right and following is not capable of doing the job here if someone's coming from the right side. And we are stopping here until we don't have a fully blocked state anymore. Now another cycle is approaching. We also predict this guy and this guy are coming from here as well. Accelerate a little bit. And I think now we should be able to go. Yeah, and then we switch to forward again. And some other guy is coming from this side who's gonna merge right into our lane now. Never mind. Yeah, so that's just quickly how this intersection zone is implemented right now. And this could also include disable swerving for the situations. That's the status on this right now.
Yeah. So,
and for the, yeah, sorry.
What information do you use for the swerving state? The yield state?
I'm using the information on if my actual lane is inside an intersection. So in an intersection zone, I've used already available functions to check the way areas. And if I'm inside a way area, then I will give this information to the behavior state machine. And this will, as a result, switch to the yielding state if we are fully blocked, if our trajectory is fully blocked, and we are inside an intersection way area.
Okay.
Right now, there's just a little bit problem that I'm just looking at the lane and not at the waypoint. So I have to look at the waypoints to define if my waypoint is inside this way area and not if my lane is inside way area. It's just something I haven't implemented properly right now. But basically, it's working. And yeah, that's the looking for just fully blocked is also something that's not perfect right now. But
okay,
basically, we're getting there.
Okay, I'm just if you, this is like just a favor, if you can prepare the summary document about like the points, the new state and why we need it, and use. This would be good to share with everyone. And also when we merge that to the repository, it's good to have a document to describe what's this merge request, so people can understand the feature and the existence of the feature.
Yeah, I'll do that. It's just like that on the 31st of March, there's the ITSC conference deadline, and I want to publish something there. And yeah, that's high on my priority list right now.
Yes, no, of course. Thank you very much. Armin, I think you wanted to present something today.
Yeah, I have a short presentation prepared as well. It's about the common road integration with OpenPlanner and automated testing. And I will share my screen really quick. Let's see. I'll go to presentation mode first. So,
can you hear me?
Really quiet, but.
Okay, and one question for Matthias. Your simulation looked very nice. What software did you use?
I'm using Prescan and Aimzen. It's a co-simulation software of Siemens SimCenter.
Could you write the names in the chat?
Mm-hmm. Yeah, and
thank you.
Yeah,
yeah, it looks really cool.
I can also give you a little bit of an overview, and yeah.
Thanks.
Okay. Any other questions for Matthias? So then I will start with my presentation. It's about benchmarking of path planning algorithms, and especially, of course, the OpenPlanner. And I decided to use Common Road, and I'll give you a quick background first, and then continue on some details. So we at the University of Applied Sciences needed a path planning algorithm, and Matthias already used OpenPlanner for his simulation. So I had the task to evaluate it in many simulation scenarios to be sure that it's the right choice for our vehicle. And therefore I got in contact with the TU Munich's Common Road benchmarking system, which has 2,300 scenarios to choose from, and supports OpenDrive map format, which would be our favorite use since it's properly documented and has all the features map. A complex map has to have. The Common Road benchmark files do use lane-led representation of a map and feature static and dynamic objects, as well as a starting position for each planning scenario and a goal position for each planning scenario. And they can be easily visualized using Python scripts and also modified. So each scenario is, has its own sub website where there's a GIF simulation running of the best submission so far to the benchmark. And there are like 700 users and 24,000 benchmark submissions, which you can compare your path planning solution or the OpenPlanner to. The current implementation I'm running for my simulation is the Common Road benchmark did only support Python, and I did add a ROS interface to use with OpenPlanner. As well as object or obstacle publisher in the Autoware format, so you can and you can interfere with them. In the ROS scenario, I am using the OpenDrive map format, which I'm converting the lanelets, lanelet representation of the common road benchmark from. And I also added OpenDrive map interface to the OpenPlanner. I had seen, Hatem, that you had the map loading flags already defined. And I did write the functions to include OpenDrive maps, at least basics.
So
and
what parser do you use for OpenDrive?
I did write my own parser for the basic features that are needed at this point.
Mm-hmm.
And it works fine. And
so
I have to think
converting
about
from Lanelet 2 to OpenDrive, right?
Yeah, for the common road, I'm converting from Lanelet 2 to OpenDrive, exactly. And I did already talk to the common road team, and they are planning on developing an entire parser by mid of this year, and I will probably help them, or at least contribute my current code base to them. And
okay, if you can share with me if it's like open, I would like also to see the like how you export OpenDrive, because
of course, yeah,
I want to add this to the mapping tool, Azure mapping tool.
Yeah.
This one you can do the opposite. You can using command line and convert from OpenDrive to Lanelet 2 or KML or vector map. So
yeah. OpenDrive to Lanelet is implemented by TU Munich as well. They have a good Python library for doing this, but the other direction isn't implemented at the moment. But they said that they want to publish this this year as well. Exactly. And then the next point is the scenario evaluation. Like after running it, you have to judge whether or not this was a proper path the algorithm chose, and whether the distances to the other objects were okay. And therefore, the Common Road team suggested a cost function in their paper published like 2 or 3 years ago. They are updating this this year as well. And then due to the submission to the Common Road benchmark, you can also compare your solution to other people's solutions, which is a nice side effect. The current limitations are that only right-side traffic is supported by my lane conversion, and that only line geometry types are supported in the OpenDrive format. I don't know whether or not you're familiar with it, but there are like complex geometry definitions like arcs or polygons available for different lanes.
Yes, this is one of the main.
This is a tough one in the. Yeah, it's a tough one in the conversion, since you have to convert it to individual points afterwards, or since you're coming from individual points, you would have to do polyfits or arc fits, which is not that easy to do.
You need to fit, and you need actually after fitting, you don't know exactly. To give you some. Because I did wrote the custom OpenDrive to Lanelet 2 converter. Yes, I supported all like different polygons, line, arc, the polynomial, poly.
Spiral,
Some people just they ignore using lines or arcs, and they use only one type. Polynomial, because polynomial you can represent line with polynomial, you can represent arc with polynomial. So they use only the polynomial to represent all the map, which make it easier, because if you want to use line and arcs, you need to check for curvature and select segments and to find and to fit
totally
several. So this is one hint. If you support poly, there is a lot of fitting functions ready, like open you can use from even if you are using PCL or another open source or even like open license library. Then just go for my idea. This is only my if you go for poly, you can avoid any issues.
I think that's a good choice as well. I think the TUM team will implement a more complex conversion, which would be able to fit arcs and lines as well. But I'm not sure, and we will see what they'll publish in the summer. But as I said, my current implementation only supports line geometry, since they they include all of the information that is provided with a lanelet, since the lanelet only is defined by its corner or edge points. And if you take a line between all of these individual points, you get a detailed enough map to drive on it. And the next limitation, which is quite severe one, if you want to do complex simulation, is that since all those scenarios are recorded, you can't react with like the other traffic participants don't react on your behavior. So you would have to fit in between those. I will show you this in a short video in the next moment. I'll just briefly show you a map of our campus, which I'm currently working on together with Matthias. This OpenDrive map is generated in MathWorks Roadrunner, and I'm already able to drive on it with OpenPlanner. And like all of these individual features are just lines with a high enough resolution to be able to display curvatures as well. And a nice thing to do would be fitting those lines, for example, for this straight part here, just fitting a line in there, and you would reduce the amount of the size of the data size of your map quite a lot. But since those text represented file formats are huge anyways, this is not of too high priority at the moment. And first things I would add are stop lines and traffic lights, which currently also aren't supported. But that's also not the most important things I want to talk about today anyways. So yeah, just for everyone to see it, this is where the map is coming from, just since the map's image is not too good. So now I'm having a few more videos. I already shared one in the Slack channel, but just for you to get a feeling of what's currently working. And I don't know whether the audio is shared as well. It's only noise. I'm sorry for that. You can see the green vehicles, the ego vehicle, the blue vehicles are the obstacles or objects, and the yellow dots are the projected lines. Everyone should know this representation of OpenPlanner. And this is a scenario published by the Common Road team, and the OpenPlanner is able to complete it. I also set up an entire simulation environment where you can automatically start a Common Road scenario. It publishes the obstacles, the start and goal position. The OpenPlanner ego vehicle automatically spawns at the start point and then drives to the end point. And there, the end state is detected, and then the simulation is shut back down.
A question,
yeah,
Armin, is can this like the Common Road evaluation be used as like if we change something in OpenPlanner, I want to make sure that it handled the same scenarios as before. Can we run as a script, as a patch run Common Road and OpenPlanner and get a number or a list of evaluation metrics to say the OpenPlanner succeeded or not?
Yeah, we can. Currently, the cost function are only provided in their online evaluation, but they already agreed on publishing them as open source as well. And then we can use them as an evaluation metric whether or not it was a successful run, which would be awesome for automated testing when deploying it to the Autoware automated driving stack.
Yeah, we were discussing with Autoware team last month about the CI, the continuous integration and testing for the on GitHub or GitLab. So we can activate that. So because it's really complicated to test a planner.
It
you
is.
can test detection, or you can test, like, there is functions with one-to-one output, but planner you need to run a lot of scenario and you need the whole stack is running. So
exactly.
So,
and I think we could do this with the common road scenarios. We could do this with or other types of scenarios as well. Common road is only a definition file, but as soon as you set up a server where you download the latest GitHub release of OpenPlanner and then run the scenarios and get back a file with the solution metrics, I think this would be quite a nice solution. You could even export like small GIF segments of those solutions in the RViz visualization, so you can be sure it worked and there was no error, and everybody can see the current performance of OpenPlanner as well. But that's just a nice to have, I think. I'll show you the other two scenarios as well. This one, it's quite a bit laggy since I'm only run this on a laptop, but it struggles there a bit with the PID control after turning left. And but since the other vehicles are currently still in standstill, it can simply turn left. I also had a version where the max speed for this lane was a bit lower, and the vehicles here started already turning left, so it had to stop and afterwards and turn afterwards. And this one is quite an interesting scenario. I will play this 2 times. It turns left here. It has quite tight turns with high steering wheel angles. And there on the right side, it slows down too much, basically, and the vehicle coming from this lane, following this our vehicle crashes into it, which is just based on the recorded positions. And a proper solution would be to add interactivity, and so the vehicles would be able to avoid our own vehicle as well. But this would as well increase the complexity of running those simulations, since you would have to run a small planning software for all of these individual softwares, for all of these individual objects.
I think you don't care about other vehicles. Like, you care about if you hit someone. Would you care about if someone hits you?
I think it's not necessary for a proper planning for testing of the OpenPlanner, since the OpenPlanner didn't hit anyone. But since the evaluation metrics of this cost function here would give us penalties if you get too close to other objects, the cost function of this scenario would be way worse than the ones, or the outputs of the cost functions for this scenario would be way worse than the previous scenarios, even though OpenPlanner did perform quite nice with slowing down for this tight curve here and so on.
So but change the cost function.
Yeah, we probably would just change the cost function or choose scenarios where there is no vehicle coming from behind. Exactly. I go on to the further steps and suggestion. Since there is no interactivity, I would like to try at least the interactive mode of common road scenarios. They do support it, and I would like to see how much the compute power would have to increase to run interactive scenarios. If it's feasible, I think it wouldn't hurt to test in interactive scenarios. Also, I would like to implement full OpenDrive maps support, including traffic lights and stop lines, since those are features that would have to be tested as well.
I'm actually interested in this point, so I can help you with my experience with OpenDrive maps.
Yeah, that would be awesome.
Yeah, and if you are okay, we can add it as a part of the Azure Map Tool converter. So
I think I will publish it open source anyways.
So yeah,
our focus is on OpenPlanner integration, and I think if we
then let's I will share with you some of the of my OpenDrive functions. There is some helper functions which can like enable you do this easily.
Okay. I think we can chat after this meeting about this a bit more. And then there is something I triggered within the Common Road team. I talked to one of their initial project developers, and they now want to include the Waymo data set as well. I don't know whether or not you've seen it, but Waymo published a motion data set on 10th of March with a new prediction and motion challenge. And it would be awesome to see all of those Waymo scenarios in the Common Road benchmark as well. And therefore, they plan on supporting those as well. And now my suggestion would be to choose or create like 100 or I don't know, 50, maybe also 1,000 Common Road scenarios that are test cases for the OpenPlanner, with interesting interactions between obstacles and ego vehicles, and interesting map scenarios with tight turns or U-turns or whatever possible. You could also just test on like 50 or 100 different maps, like with left side and right side traffic, and add like a different start and goal positions to all of these individual maps. So you wouldn't have to create as many maps, and use them as a reference for integrated testing or unit testing of the OpenPlanner whenever new software releases are made. That's it from my side, and I'm open for questions or whatever suggestions.
Yeah.
Thanks.
Thank you. That's really nice, actually. You can test it, and we can add the changes for OpenPlanner 2.5, and we can have a comparison results between how the current one and the modified one is doing on the benchmark. So that's a really good way to test the changes, and also compare it with other planner. There is a planner. I don't know if you can, the new Autoware architecture proposal. You can compare with that. There is another planner there.
Yeah.
They call it Autoware.pilot or Autoware.iv. So you can also compare with that.
Yeah, exactly. And the only thing I think we would have to agree on are the simulation model. Since currently I just implemented a single track model or bicycle model, and without any acceleration or deceleration limits. I think the same as you have in your OpenPlanner sim. I think we might want to increase the complexity of this model to be able to run realistic parameters that would be feasible for real vehicles as well. Since then everybody could just download the OpenPlanner and like launch a script with a parameter set that is already tested and could at least perform decent with a real vehicle. So there wouldn't be as much effort for tuning afterwards.
Yeah, actually, we need to do that. But from my experience, each car, when you try to Autoware and generally an OpenPlanner, especially on a new car, it's a bit challenging, and you need to tune a lot of parameters. The problem is sometimes we change OpenPlanner or Autoware, and the controller itself has to be tuned. So one thing I want to make like write an article or video or something is how to identify the core issue. Sometimes we over-engineer and we solve the issue. I do that. It happened. I do a solution in OpenPlanner, and then after testing in different maps in different scenario, or testing with Carla simulator or on a real car, I find it's not a problem with the OpenPlanner, and my solution make it worse. It's a problem from, for example, object detection, from tracking, from localization. So fixing a bit these kind of issues, identifying the issues, actually the more important than fixing the issues. So yeah, thank you very much, everyone, for your valuable presentations and comments. We agreed we will have, I will leave Matthias to finish his paper, and Max, I expect he will try the new one, OpenPlanner 2, and maybe give me a feedback. And Armin, we will discuss about the OpenDrive converter later. Anyone has any comments? Any comment, question?
No, I'm fine with what you said.
Okay, thank you all. We will meet in 2 weeks. Thank you very much.
Bye.
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 Thanks. Bye.
See you.